Good afternoon, everyone. Thank you for coming to this. Actually, it's the last talk of the tutorial series that we've had since the first day of the conference, and we're ending the tutorial series today. There were 11 tutorials, and this is the final one. Today's our tutorial presenter is Professor Hui Yang, and he is professor in the Harold and Ing Marcus Department of Industrial and Manufacturing Engineering at the Pennsylvania State University. Dr. Yang also currently serves as the director of the Penn State National Science Foundation Center for Healthcare Organization Transformation, also abbreviated as CHOT. Dr. Yang's research interests focus on sensor-based modeling and analysis of complex systems for process monitoring, process control, system diagnostics, condition prognostics, quality improvement, and performance optimization. He has received numerous prestigious awards and grants, and he has received especially the National Science Foundation Career Grant. He is also a fellow of the Institute of Industrial Engineers, Institute of Industrial and Systems Engineers, the IISE Society. And he has served on various prominent editorial positions in several journals. He has also co-authored the 2016 book, Healthcare Analytics, From Data to Knowledge to Healthcare Improvement. So I will allow Dr. Yang now to present his tutorial.
Good afternoon, everyone. First, thank Harry for the introduction. And I would like to acknowledge the editorial team of Inform's tutorial and the wonderful editorial team. And it's my great pleasure to present my research, mining nonlinear dynamics in operational data for process improvement. And for codes and details, and please see this paper. And the source code, the links, and open source MATLAB toolbox are available in this PDF and in this paper. So this is the outline of today's tutorial talk. First, I'm going to talk about advanced sensing and how it is related to industrial engineering, and also how to go from sensor to process monitoring, process modeling, and process control. Then I will dive into nonlinear dynamics, logistic map, geometric thinking, and Taken's embedding theory. And after that, I'm going to talk about recurrence theory and also self-organizing network. And in the end, I will conclude this tutorial. So first, please allow me to introduce Penn State Industrial Engineering. So this is a plate in the campus, which shows Penn State IE is the nation's first academic department for bachelor degree and established in 1909. So our first department head is Hugo Daimer, and also he's a close colleague and friend of Frederick Tyler, father of scientific management. I want to highlight Frederick Tyler, who is basically, people also call him the father of industrial engineering. So there's a very well-known book called Principles of Scientific Management. So why scientific management? Because in the book, Frederick Tyler advocates or strongly recommended the data measurement. For example, the timing of every job that we accomplished in the manufacturing plant. So he emphasized the data measurement and the integration with manufacturing engineering. So this book marks the debut of industrial engineering. So let's have a look at the sensing before in 100 years ago and the sensing today. Obviously, they are very much different. And sensor today, we have wireless sensors and supervisory control and data acquisition systems. So complex system lab is a lab that I run at Penn State. And in the complex system lab, I run two parallel research programs. One is manufacturing, the other one is healthcare. So manufacturing research program is primarily funded by NSF, and recently healthcare program funded by National Institute of Health. But we focus on going from sensors to models, and then to the decision making, optimization of the systems. And the theoretical foundation is nonlinear dynamics, and which I'm going to talk about how to mine nonlinear dynamics in operational data, and statistics, signal processing, simulation optimization, and control theory. So here's an example of advanced sensors we are using today. This is my first project. I worked with General Motors, and General Motors actually have a lot of programmable logic controllers, which connect a lot of data and control the process in the assembly line. And we pull the data from the automotive assembly line and then build simulation models based on the data. So this is first set of sensors and in the manufacturing plant. And this is the second set example from ultra precision machining. And as we can see, this is what I did before with acoustic emission, vibration, and cutting force sensors. With all the sensors, we can control the process and especially the machining surface. We want an ultra precision finish of the work pieces. And recently, additive manufacturing, digital manufacturing, in order to control the process and also increase information visibility, we put spectrum sensors, high-speed videos, and layer-wise imaging, and acoustic sensors in the additive manufacturing machine. And recently, I just finished my sabbatical from Fulbright program. In the Fulbright program, this is what I did in the Fulbright program, and we have laser powder bed fusion, so metal powders, and then we use laser to fuse one layer of the powder to form one layer of the metal parts. But we had a new idea, and what we know when we do the document print, and we can also do the scanning. We have document printer and scanner in one. But currently, there is no metal 3D printer and scanner in one. So what I proposed is to leverage the contact imaging sensors. It's the sensor we have in the document scanner. I put it over here. So every time when we finish one layer of fusing, then we can also scan this layer to see the quality that we have just fabricated in this layer. Yeah. So detailed information are available in these two papers. And this is another example of advanced sensing in healthcare area. So this is a simulation model I developed for human heart and electric wave conduction and propagation through the human heart. And also the pharmaceutical engineering, and we collect a lot of data in the process. And one classical example is the sweetheart problem. Because I had one NSF project specifically focused on the diabetic complications on the human heart. And then I studied how glycosylation, basically the sugars and the glycosylation process, how does it impact the ion channels. And some of them, then the ion flow got impacted. Then the heart, electric conduction and propagation also got impacted. And then how do we design drug to counterbalance this diabetic effect? And definitely we know EKG, which stands for electrocardiogram. And we can connect EKG from the heart and see how heart is responding to the treatment and to the surgery, and also how it is functioning. And we can do the variable monitoring of the heart. And recently, during the Fulbright program, and I wrote a book and with my PhD student, Bing Yao, who is now an assistant professor at University of Tennessee, Knoxville. And I focus on the concept sensing, modeling, and optimization of cardiac systems. I'm a strong believer that we should connect OR theory with front-end sensor connections and also statistic models, and then a coherent framework of sensing, modeling, and optimization of manufacturing or healthcare systems. So we have complex systems in manufacturing or healthcare. Now we put advanced sensors, Internet of Things, and wireless sensors, supervisory data acquisition, and control system. And now we have operational data. And now we call it big data. And when it's big, we want to extract useful information from the data and also derive new knowledge so that increase our understanding of the system and then help us to optimize our decisions. But naturally, we love and accept synthetic data, linear, stationary, clean, continuous data. Sometimes we call it curated data, and data is not well curated. All data are not clean. However, in the real world, in many cases that we are facing, the natural systems, they are highly nonlinear, non-stationary, and with noise and intermittent switching behaviors. And yeah. Now let's dive into the nonlinear dynamics. There is a need for us to look into nonlinear dynamics in the operational data. So dynamic system is a rule for time evolution on a state space. So what is a state space? Let's first define state space. State space is all possible states of the system. And then the state is a d-dimensional vector defining the state of the dynamic system at a fixed time t. And we can represent the state with a d-dimensional vector. The dynamics or equation of motion is x dot equals to fx. F is the mapping function. So mathematical function of state variable, which tell us what's going to happen in the next step. So dynamics describe the causal relation between the present state and the next state in the future. So linear dynamics, the function relationship between subsequent states is linear. So this is linear dynamic system, and the system's evolution is linear. And as we can see, we can represent this with a matrix A, and if the initial condition is given, then we can derive analytically the general solution. And the solution is explicitly known for a time t, and the stability of linear dynamic system is determined by eigenvalues of matrix A. While the nonlinear dynamic system is difficult or sometimes impossible to solve analytically. Now we have a complex function f which is nonlinear. So components are interdependent. So x, y, z components are mixed. For example, in this one we have x, y, z, and x. So this is Lorentz system. And but we see there are multiplication of two components, x and z, and x and y. And here we see that in the Rossler system, this is a trajectory, or you can call it state space, and we can see the state space trajectory. And this is a Rossler trajectory, and this is a Lorentz trajectory. So Lorentz system is widely used for weather forecasting, while Rossler system is used to model equilibrium in chemical reactions. Just now we looked at three-dimensional complex system, nonlinear system. Now let's have a look at one-dimensional. I will give you an example of one-dimensional. So first, the linear system. So xt plus 1 equals to rt, rxt. So every generation, the population of fish in a lake grows by 10%. So xt is the population of generation t, and 1.1, let's suppose, give a parameter 1.1 is the constant growth rate. Then we can, if we were given the initial population x0, 100, then we have population 100, and next generation 110, 121. So this can be solved. And we can also see if we have exponential growth, and this is also linear, we can analytically solve it. But now let's have a look at nonlinear relationship, that is the logistic growth. So logistic map, I have to emphasize, logistic map is different from logistic regression that is commonly used in data mining. So logistic map is a one-dimensional nonlinear system for logistic growth. As we can see, we no longer assume the constant growth rate, but the growth rate in general is proportional to the remaining capacity. So that's R1 minus xt. So which describes the behavior of a population that has limited resources and food, water, or space.
So linear growth, exponential growth, they are predictable systems with analytical solutions. But nonlinear dynamics, sometimes it's not predictable. I'm going to show you. If we have R, you see here, R equals to 2.8, R equals to 3.414, R equals to 3.5, or R equals 3.8. They have totally different behaviors. The system has different behaviors. And as we can see, if we have different initial conditions, during this parameter, I equals to 2.8, it converge. And however, this oscillate periodic 2 and 0.1, 0.2, 0.3 initial conditions. But when it goes to 3.8, and the system is getting a little bit chaotic. Now let's study the possible states of this system in the long run. How does it relate to the parameter R? And this is a logistic map. At the x-axis is the growth rate, R. When we change R, the system, the attractor, this is the possible long-term values of the logistic map. As we can see, when R is in the range from 0 to 1, and we have extinction system. And then we have steady state system. It converges to a constant value. Then we have periodic 2, and then periodic 4, and then we get into the chaotic region when R is greater than 3.5 and approaching 4. And a slight variation of R, 0.001 to 0.002, it will give big variations of the system behavior. So there's a red rectangle over here, and let's zoom in to see the system behavior, long-run behavior. As we can see, this is a zoom-in version from approximately 2.8 to 4. As we can see, if we zoom in, we see a very similar picture as before. Now, let's zoom in again into this region. So this is from 3.4, approximately 3.4 to 3.6. And this is the zoom-in version. See, this is what people call self-similar behavior, or the fractal behavior. And the source code that I wrote to generate this example is publicly available in the MathWorks or website. I just downloaded into the file exchange. So let's summarize. In logistic map, a small difference in the value of R, or initial value x0, can make a huge difference in the outcome of the system at time t. No formula can tell us what x will be at some specified time t, even if we know the initial condition, and especially in the chaotic region. So the system is unpredictable. There are sensitive dependence on initial conditions. So what we have seen here, the red one, is a biofunction diagram, which gave us possible long-term values of a system as a function of the biofunction parameters in the system. So far I covered the linear dynamic system, nonlinear dynamic system, and what do we mean by nonlinear dynamics, and with three-dimensional example and a one-dimensional logistic map example. And we have seen the biofunction diagram and also the fractal behavior, and what do we mean by chaos. And also, now, if we have a nonlinear system, how do we analyze this nonlinear system, which requires geometric thinking? And the way we analyze the nonlinear dynamic system is different from traditional way to do the time series analysis. So traditionally, if we look at the time series, for example, the EKG signal in the top panel, and we look at the time domain. So x-axis is time, and then we see the signal variations. In nonlinear analysis, we do the time delay embedding, and we put xt in this x-axis, xt plus tau and xt plus 2 tau. Then we will be able to reconstruct the state space trajectory. Then we could look at the shape and the topology of the EKG trajectory instead of just use the traditional ARIMA or ARMA model to analyze the time series. So in this state space trajectory, we can study the divergence of the two trajectory, and then we can see the point care sectioning, and then what is the distribution in a particular area or a particular cross section, and also how they diverge. Then we can derive Near-Perloff exponent. So that's how people do the nonlinear dynamic analysis. So this is fundamentally different from traditional time series analysis. In nonlinear dynamics analysis, people look at the trajectory and the state space, high-dimensional state space. And people often ask me a question. So we have EKG time series. We can see very straightforward information. Then why do we need to embed it in a high-dimensional space? Or why do we need the geometric thinking? Now I'm going to give you an example. So an engineer observes a specific signal, but this is a flatlander view. Okay, and if we follow traditional time series or traditional data mining or stochastic modeling, how are you going to model this when we capture this signal? And we may be wondering what's going on the back end which generated this signal. As we can see, there are different frequency and also different bandwidths, right? And there are different timing that a particular color appear. And guess this kind of signal and how we should do it. Maybe there are transitions. We should do a Markov model, right? Maybe we should do the statistics, see how often they appear. That's a traditional time domain analysis or data mining approach. But if we take one step back and put this in the higher dimension, let's see what's going to happen. This is actually the system behind the signal. And this is Plato's universe. And what we see is just previously what we see is just a flatlander view. Now I hope I give you a better idea why we need to have the geometric thinking that is proposed by Poincare to study a nonlinear dynamic system. If you have a time series, how do you, or operational data, multidimensional, how do you embed it in the state space? So this will come to the Taken's embedding theory. The state space trajectory can be reconstructed from a time series by the time delay embedding. That means if you have one-dimensional time series, you can delay this time series by tau, and then you get the second dimension, and then you continue to do it until you reach d-1 dimension. So from xn plus 0 tau to xn plus d-1 tau, in total we have d dimension. So the embedding dimension is actually optimally determined by a method called Fell's nearest neighbor for d, and time delay is determined by mutual information. As we can see, this is the time domain signals of EKG, and we can put it in the time domain, and then we study the examples. But the right-hand side is the state space trajectory of the EKG signals. So we can study the shape and topology of the trajectory. And the source code to generate those ensembles and the state space trajectory are available in this link. So now let's have a look at how to capture the time delay. So if the time delay is too small, a tractor is restricted to the diagonal of the reconstructed phase space. If it is too large, components are uncorrelated. Reconstructed attractor no longer represents the true dynamics. So the general approach, the heuristic approach, you can do visual inspection. Just try a few tau values and then look at the state space. And to see whether the tractor is or the trajectory are spread out. And the disadvantage sometimes is satisfactory results only for simple systems. And another way to do it is to use the autocorrelation function, and because we can study how the data autocorrelation is autocorrelated. So optimal tau requires a linear independence, and which is the value when the autocorrelation function first passes 0. But this is linear correlation. Sometimes system has nonlinear correlation, so which comes to the mutual information. So as we can see, this is a definition of mutual dependence of two variables. So x and y, and we have joint distribution and probability x and y, and log probability x and y, and then marginal distribution px and py. So where x and y are two random variables, px, y is joint mass function. Px, py are marginal functions. So this definition, mutual information, is derived based on the entropy, so px log p, and a joint entropy pxy log pxy, and a conditional entropy. So then we have this mutual information. Now, this mutual information function is available, and I have coded it in this toolbox, and you can call this specific function and see how it works. So practically, how do we calculate this Rxy based on joint and marginal probabilities? So here's a practical implementation. If you have the two variables, x and y, and we know we can get the marginal px, and we just project it into the x dimension, or the marginal of py. So pxy is at x and y location, and how many appearance of the data points inside a particular box, and then you divide by the total number of data points. So that is the joint distribution, number of points in box x and y divided by total number of points. And then if we plot the data in this way, then we will be able to derive the mutual information. So embedding dimension, D. So optimal embedding dimension help us unfold the attractor. So the minimum dimension is required to reconstruct the system without any information being lost, but without adding unnecessary information. A larger dimension than the minimum leads to excessive computation when investigating the dynamic properties. For example, I have a 3D cup over here. If we put the 3D cup in the 4-dimensional or 5-dimensional, and we didn't lose any information, but we actually add excessive computation because we add extra dimension. So noise will populate and dominate the extra dimension of the space where no dynamics is operating. So here, I give an example. This is a trajectory, and if we project this into the 1-dimensional, just like the flatlander view, then this is a 1-dimensional view of this trajectory. Okay, so false nearest neighbor. What is false nearest neighbor? The idea is to measure the distance between a state and its nearest neighbor. As the dimension increases, this distance should not change if the states are really nearest neighbors. So for the previous trajectory, if we project this into, for example, ABC, if we project into the 1-dimension, as we can see, who is the true neighbor of A? So we have a point A here. So obviously C is the true neighbor, but when B is projected to the 1-dimension, B becomes the false neighbor. False neighbor, that means because we projected into a lower dimension, then this data point B, originally it is not a neighbor of A, but when we project, it will become a neighbor of A. So what we do is we go from 1 dimension to 2 dimension until we find that the false nearest neighbor number is decreasing. Okay, we don't have more false nearest neighbors. So any object, 3D object we have in the room, we can project into 1 dimension. We will have a lot of false nearest neighbors. But if we expand it into 2-dimensional, we will have less. 3-dimensional pretty much is fully expanded. In 4-dimensional, we also have less nearest neighbors, even if this object is 3-dimensional, right? So we need to test different dimensions and see how many, what is the proportion of false nearest neighbor we have when we put this system in a particular dimension. So the false nearest neighbor source code is also available in this toolbox. So the general computation is, suppose we put this xr is the r's nearest neighbor of xn in the d-dimensional space. And the Euclidean distance between this xr, n, and xn, this is the distance in the d-dimensional space. Now we are going to increase one more dimension. That means we're going to add d. You see here, this is d minus 1, right? From 0 to d minus 1. So in total, we have d dimension. Now we're going to go one more dimension, that is d. And then we get the actual calculation of the neighboring calculation. We want to see how much change we have. This will become false nearest neighbor criterion. We can now look at the relative change in the distance as a way to see if the states were not really close together when increased to a higher dimension. So far, we talked about if we have time series, if we have data, why it is necessary for us to look at it in the higher dimension or have a geometric thinking, and how to put the data into the higher dimension, that is Takens embedding theorem. Now let's look at it. If we put the data in the higher dimension, how do we look at the behavior of the system? That is the recurrence theory and the heterogeneous recurrence analysis. So point K has recurrence theorem, and which states that T be a measure-preserving transformation of a probability space. And then for any natural number, n belongs to the natural number n, the trajectory will eventually reappear at a neighborhood A of former state. Okay, so that means this x belongs to A, and then t steps later belongs to this space, but it does not belong to A, is actually the probability is 0. That means eventually it will reappear in the neighborhood of A. And that will also be the first return, that is a minimum n. It comes back to the neighborhood of n. And recurrence behaviors are very common in our nature. For example, in the manufacturing, we have power consumption signals. We see some recurrent behaviors when we just process the workpieces. And also we can see the human heartbeat, one beat, next beat. There are recurrences. But there are aperiodic recurrences, and also there are recurrence variations, which help us capture the system behaviors and also the anomaly and disease in the human heart. And if we look at another example, every year around October, this time we come back to informs. That's a recurrence too, but not strictly at exactly the same date, right? So recurrence plot, as we previously discussed, we put the data in a higher dimensional space. Now, in higher dimensional space, if we look at a state, and if we put a circle over there, and we see some neighbors or recurrences, and because that's neighborhood A, and we see some coming back, some states after a while it will come back. So the recurrence plot represents those times at which the system recurs to a former state. That is, a trajectory visits the same neighborhood in the state space. And this is a state, and we can go into different areas, and then we come back. This is a recurrence. And this is another state. For example, this is a state. And then when it is come back, I will mark another dot over here. I will say the system actually returned to this neighborhood. And how do we get the trajectory? We can do, if you have multi-dimensional signals, you can use real-world signals. And if you have single-dimension signals, you can do the Takens embedding of the state space. So let's have a look at this recurrence plot. The x-axis is a state. Y-axis is also a state index. And if we pick a state in the x-axis, for example, 400, if we go vertically, we will be able to identify those states that return to the neighborhood of state 400. And if we go to another one, 800, we will see the return of all the neighbors of state 800. So this gives us a way that we characterize the state space and also the behaviors of the state space. So there are very intriguing or interesting patterns in the recurrence plot and structures. As we can see, if we have periodic systems, and like a sine, and we see strict lines, and because we keep coming back and deterministically. And if we have Lorentz time series, and we see intermittent behavior along the diagonal lines, that means the periodicity is disrupted. and we see some breakup of the diagonal lines. And they are intermittent behaviors, and also sometimes there are vertical stability or vertical delays in the states transitions. But if we have a random noise, you see we have a very random system. So the small scale structure, that is the single dots, diagonal and vertical lines, diagonal lines and vertical lines. So large scale structures are homogeneous and periodic disrupted patterns, which tell us a great deal of information about the periodicity, noise, intermittent behaviors, and homogeneity and non-stationarity. Because if there are very strong vertical lines, that means we are shifting into a new regime or area of the state space. But we talk about the recurrence, and then we get started to study recurrence, and we found that there are different types of recurrence. Because previously we talked about recurrence can happen at different areas of the trajectory. How do we, and if we treat them all as black dots, right? So they become homogeneous. So for example here, we have two pairs of recurrent states. So from 15, 17, 19, they recur 1, 3, and 5. So one state X has 3 values. We have 3 dimensions. This is a recurrence. But this recurrence is very much different from 32, 34, and 36, and then 30, 32, 34. So they are different recurrence types, type 1 or type 2. So how do we capture this different type of recurrence? Then we were thinking about, we got to have a new idea, which is called space indexing. We want to see which area my system is evolving into, and we want to count at that specific area how many recurrence we have, the degree of recurrence we have. Then we borrow an idea from database management, because they are multidimensional data indexing, which helps speed up data retrieval and data query in very large database. And then we said, why not? We do the state space indexing using the tree, arc tree, and then we can separate the state space into different areas. Then we can mark them. Now after that, we can map each state xn into a k belongs to a set of areas in the state space. Then we do the iterative function system. That is, we give each state an address, cxn, cyn, which is based on the previous state, and also based on where they are. The k is where they are, which area in the state space they are. And then we do a little bit of shift of the previous address, and also plus the area that they are, sine and cosine, so that we can have a circular diagram. So initial address is 0, 0. So let's have a look at this example. So in the y-axis, you see here we have 1, 2, 3, 4, 5, 6 to 8. We have 8 areas or 8 regions in the state space. And now when the system is evolving, right, in the state space, when it comes to the region 7, so the system getting into region 7, then I give an address, and here is this address is, and we give initial address 0, 0, and now this is the first point, 1, 1. So what we have is 0.1, 0.1, 0, 0, and then we know this is in the regime 7. Then we have a sine cosine. And now we got the address of the first state is over here. Now, when it comes to the 6th, the red means the current state. When it comes to the 6th, we are entering the region or the region 6. Now, we know the previous address, 0.707 minus 0.707. Now we put it in because it's based on, the second state is based on the previous state. And also based on where it is right now, 6, right? So this is area 6. And then we got the new address. right here. Then we continue to do it. This is 3. Then this is a 3. And we continue to do it. 3 again. You see, although these two states, both of them, they're entering region 3. But they are slightly different. Why? Because the fourth, this is CX4, CY4, is actually dependent on the previous state. We have a slight deviation in this region. So if we continue going, and then the IF address is unique for every state. Two states have the same address if and only if they share the same categorical variable, or the same, they are entering the same region, and all of their previous states are the same. Okay, so this is the IF transformation, or we can call it a fractal diagram, because if we zoom in, it will be another circular diagram. You see here, this is a Markov process, and then we generate a series of data. Now let's see, we have 1, 2, 3, 4, and then to region 8. Now, if we zoom in 8, we got 1 to 8, 2 to 8, 3 to 8, and we got another circular diagram. As you may see, this is self-similar behavior, and this also gives us fractal view of the data. And if we want to look into it, we can continue to dive into the diagram. We can see 1 to 8, 2 to 8, 3 to 8. And we can continue to zoom in. If we have enough big data, then we can keep zooming. So what you can capture is single state distribution, 2 state sequence transition, 3 state sequence transition, and a 4 state, and then you can keep going. And this is very useful for us to check the system, especially monitoring the system. So because we have the diagram, and we can quantify the variation in those IFS diagrams. So what we did is, first, how many of them in a particular region? State 1. K1, K2, KL. This kind of transition appear how many times? And also recurrence rate. This is a heterogeneous recurrence rate. And this is the cardinality. And these are the set. The first one is the set. How many of them in different areas? What time do we appear in this state sequence? And also this is the rate. This is the mean in each area, and this is the entropy, the distribution in each circle. So because we got the recurrence quantifiers, now we can do the process monitoring, use those quantifiers. But traditionally, we assume the variables are independent, but sometimes they are correlated, they are dependent. And then if we know the mean and the covariance, then it will automatically follow chi-square, but we have unknown population mean and covariance. We have to estimate it from the data. So we know the sample covariance and sample mean, and replace the population mean and the covariance with sample mean, sample covariance. So, and then we will be able to, what if the sample covariance matrix is singular? Then we can add a particular variation into it. And the detailed information how to tackle the singular problem is available in this paper. Yeah. So now let me take one step back, how to apply and connect with engineering applications. This is a manufacturing example, ultra-precision machining. As we can see, there are signals, acoustic emission, vibration, and cutting force. And we have this paper detailed the development of heterogeneous recurrence monitoring of dynamic transient in ultra-precision machining process. And when we machine the surface is in good quality if the surface finish is within 100 nanometers. As we can see, the left is a very flat surface, and the right is greater than 100 nanometers. And so we got a rough surface, and we want to study the difference based on the sensor signals. And then based on the data, sensor signals, we will be able to extract, and we can plot the transitions, and based on the transitions, we can extract the recurrence behaviors or the quantifiers. Then we can see that this is a traditional method, top panel, A and B, and this is what we have for the heterogeneous recurrence. We can see when RA changes, traditional methods cannot distinguish from the sensor signals. However, the new method can distinguish the behavior, the surface finish variations from the sensor signals. So here is another example for the cardiac system. You know, when the human heart is beating, we actually have EKG signals. But people often think, oh, EKG signal is just one-dimensional signal, but a heart is a three-dimensional heart. When heart is beating, the electric wave propagates in the three-dimensional space. So if you only take, for example, a variable sensor, you only get a one-dimensional EKG. That means you are looking at a person or the heart only from one angle. So if you want to get a comprehensive idea about the heart, you got to look at the heart from multiple angles. So that's why if we only rely on one-dimensional EKG, sometimes we can miss very important disease or the cardiac events. If we look at the trajectory, if there are like a disease actually varies the trajectory in the space, because you can think if there's damage in the heart, which actually pushes the electric wave to a different direction. So the trajectory actually changes. So if we use the heterogeneous recurrence rate, then we will be able to tell the cardiac event detect very quickly. Those are the example of heterogeneous recurrence monitoring. Now, so far we finished the nonlinear dynamics, a brief introduction of nonlinear dynamics, and why we need to look at the state space trajectory, and also the geometry of the state space trajectory. Recurrence is one way to look at the trajectory and the geometry topology in the state space. There's another way called a self-organizing network, and let's get into a new concept, self-organizing network. So network analysis, for some time we have known topology. We know who is whose friend, and in the social network, and you can extract those data because they are linked, they are followed, right? And in the computer network, and we have hard wires, all the Wi-Fi, we connect all the computers together. And in disease, and we also have different variations, and they are connected in COVID-19. So network representation, the adjacency matrix A is a means of representing which nodes of a network are adjacent to other nodes. If node I and j are linked, we give a 1. If they are not linked, we give a 0. So that's Aij. So network statistics help us statistically quantify the physical networks. But if we know the network topology, we can get the adjacency matrix. But now, if we have the adjacency matrix, can we derive the physical topology? So this is one paper that we published to answer this question. So if we have a time series, so how do we derive a network? There are two different ways. So give a time series. We can reconstruct the state space, and D is the embedding dimension, tau is time delay. And if we assume a node xi is connected to its k nearest neighbors, but excluding the nodes in the same strand of the trajectory. So this is called stellar window. You see here, this node is connected to k neighbors. This node is connected to k neighbors. Then we can derive a network, and also the adjacency matrix. However, but previously the number of neighbors is fixed for every node, because every node got k neighbors. But this one is based on the recurrence. That means if we draw a ball around this state, we will be able to find the neighbors. But at a different area, we might find less neighbors. So the recurrence are treated as links in the network, and the adjacency matrix is obtained from the recurrence matrix by removing the diagonal identities. Okay, so this is the new recurrence network. So once we got the adjacency matrix K, adjacency matrix A, Aij, we will be able to derive the node degree, Ki. Ki is the number of neighboring nodes of node I. If we look at the adjacency matrix, and Ki equals to the sum of all the j, and the ij pretty much all the rows. One row in the adjacency matrix, the first one, node degree. Link density is the ratio of the number of edges to the number of possible edges. So that means Aij, and because there are so many links inside the Aij, and we just count how many ones we have in Aij, and then divide by total number of possible edges. This will be link density. Distance, Dij, is the minimum number of edges to travel from node I to node j. Okay? And the average path length is the average of all paired distances, Dij. So diameter D is the longest of all shortest passes. Clustering coefficient of node is the probability of two neighbors of a node I are also neighbors. So as we can see from the definition, most of the network measures or metrics, they are derived or calculated from adjacency matrix. So for example, if we have this network, and we can see for every node, we can calculate the node degree. So the distance between node A and B is 6. That means travel 6 edges. I will be able to travel from A to B. So average path length is 2.3210, and the clustering coefficient is 90% for node 1, 0 node 20, and 100% node 27. So average clustering coefficient is 62.7. But those, we only, in the adjacency matrix, we only count 1. We only have 1, 0. The network measures, can we not based on 1 or 0, but use the actual node-to-node difference? And if we want to use the actual node-to-node distance, then we have to derive the network topology from the adjacency matrix. That means give you an adjacency matrix, tell me what self-organize a topology for me. But adjacency matrix, you see, is 0 and 1. How can we go from adjacency matrix to topology? So we could have, for the same adjacency matrix, we could have a variable of topologic structure for the network. For example, these two, the link, they are the same, right? They are all derived from the same adjacency matrix. But the shape is a little bit different. Which one should we use? Right? Is there a unique and stable topologic structure for a recurrence network? And this is studied in this paper. And for details, you may dive into technical details. You may dive into this paper. But I'm going to show you an example how to derive the network topology. As you can see, this is an adjacency matrix. Okay, this is the adjacency matrix. And now these two are self-organizing. As you may notice, they start from different initial conditions. But the connections, they all follow this 0 and 1 pattern. As we use the self-organizing algorithms to organize the network, you see the energy actually drops when the network topology is starting to form a shape. And when it converges, we will possibly see a same topology. But let's see whether they are the same. So for an adjacency matrix, the self-organizing approach yields a unique and a stable network topology structure by minimizing the system energy, even from different initial settings. As we can see, we approximately reach this plateau phase, and this adjacency matrix gives us a very interesting butterfly shape from two different initial conditions. So that means we could do it, right? Now, how could we use this in the engineering design? You know, very interesting. Self-organizing network recovers the geometry of 3D design. So which disclose the geometry of a recurrence network, provide a new way for optimal matching and retrieval of engineering designs. As you can see from the random initial setting, as we evolve, it will become a chair. Now, if we can capture this in the network matrix, you see, it will become linear algebra, and we can match different design in the database instead of doing deep learning of the 3D point cloud. You see, it is getting very, very easy to use and easy to retrieve and easy to match 3D designs. And now let's see an animation, how this self-organizing process works. From the initial conditions, we see it actually self-organizing into a chair. So the self-organizing process of recurrence network for a chair, and this animation is available in my YouTube channel. And so this is for the computer chair. And people may be wondering, if we change to a different design, will it still work? Okay, now let's look at this. What is this? It's random, and we haven't figured out what it is yet, right? So, but it's dancing. It's dancing, and then it emerged to be a very beautiful dance. And this is an ant. So self-organizing process for an ant. And because ant has a lot of angles and feet, so it takes longer time to self-organize. Because the more complex the geometry is, and the longer time it will take to reduce the energy. And this is another example of the drone. And we also start from the random layout, and using the recurrence network approach, we will be able, and leverage the self-organizing algorithms, we will be able to reconstruct the 3D designs. And the detailed algorithm is available in the paper that we just referred in the previous page. So far, I talked about a brief introduction of nonlinear dynamics, and then we dive into recurrence theory and heterogeneous recurrence theory. And then we talk about self-organizing network. And we covered a few these topics, and most of the demos and the links are shown in this slide. And also, you can find those links in the PDF tutorial available in the Informs website. So at the end, I would like to acknowledge editors, Doug and Harry and Ibru, and anonymous reviewers, and the wonderful editorial team I have worked with. And I'm so glad I have the pleasure and the opportunity to work with you guys. At the same time, I want to acknowledge my advisor, Dr. Satish Mukhopadhyay. I learned nonlinear dynamics from him. And my collaborator and also my mentor when I was assistant professor, Dr. Eric Bennett, and wonderful students and I have worked with, all the PhD students in my lab. And yeah, some of them, they are tenured associate professor and now tenure track assistant professor. So far, my lab has graduated about 8 tenure track assistant professor and 1 tenured associate professor so far. And I anticipate maybe in the next 2 years, we will have more tenured associate professor from my lab, yeah. So, and also I would like to acknowledge my sponsors from NIH, NSF, and without, and also industry partners. Without their support and collaboration, and this work would not be possible. So here is my contact information, and I will be happy to talk more in details and answer any questions you may have. Please feel free to reach out. Thank you very much.
Thank you. It was I really enjoyed the presentation, and there was I think the first sort of thing that occurred to me, that there was some sort of sense of mystery or wonder that sort of permeated the talk, and that came through all the examples. So something very interesting. Yeah. So let's open it up to the audience first. If anybody has a question, I can bring the mic over and.
Maybe this is a redundant question. Fascinating what you're doing with the self-organizing. Can you explain in layman's terms, I'll say, how you get I can understand how you take the connectivity matrix and that produces something, but like when you produce a chair or an ant or a drone, how does it get the distances between those related and the unrelated pieces?
Oh, that's a wonderful question. What a
Okay.
wonderful question. Yeah, and that's a big question. It will probably take another talk to answer this question. But briefly, I think self-organizing algorithms actually leverage the connectivity and also the connections among all the dots, all the nodes. And because the nodes, the adjacency matrix already capture those topological information. So what we did is just reconstruct it through the self-organizing algorithms. Because, yeah, by reducing the energy. But as to the details, how to reduce the energy and how to calculate the energy and also how to optimally choose the parameters, those are very technical details. And I do have a very detailed paper in many pages, and I could share with you, and then we can talk more about the self-organizing and network and how it can be applied into different areas.
Related question to that, again, from a basis of complete ignorance. If it's self-organizing, and you talked about starting with I'll say a random cloud of points. So would this give you a method for saying I've got this connectivity matrix, which took measurements from, I'll say, this perspective, and another connectivity matrix that took measurements from a different perspective, and then say, since these self-organize into the same result, could you do a comparison at the raw matrix level and say they're really the same thing? And would that give you like a vision recognition system or something like that? I'm really jumping off into space on you.
Oh, yeah, that's exactly what I am actually proposed to do. Because my goal is not just self-organizing. My goal is actually using this for provide a new way for optimal matching and retrieval of engineering designs. Because in this world, you see, we have deep learning of the image, right? Deep image, they are very regularized data. But Google has image search, has text search, but it's you may not see the 3D data search, right? 3D or 3D object search. It's very difficult to implement at this moment. And what I propose is, just as you visioned, that because the matrix, right, we can capture the matrix. The matrix actually reduce the dimension from like 3D design to the 2D, and then all the linear algebra can come into play and help us to optimize the match and retrieve of 3D design. And in other words, if you have a chair and you want to search a similar chair, you can just throw it into the search engine, and then it will be able to derive like a two-dimensional connectivity matrix, and then it will be able to match all similar chairs and then provide the feedback to you.
Excuse me, it's fascinating stuff. So the connectivity matrix, like, do you start with 2 or 3 pictures to get the three-dimensional buildup, and then you say this point has a gray connection to that point, therefore they're connected, or this point is touching white space, so they're not connected? Is that kind of how it builds it up?
In industry, there are different ways to do it.
Okay.
Because the front-end sensing, there are different ways. There are industry scanners, and there are image-based 3D reconstruction, and yeah, the LiDAR sensors. And I was amazed in the Phoenix Street. I saw the Weimar, and they have LiDAR sensors rotating, right? So they all give you 3D point cloud. And what I propose is we leverage this kind of data, and then we can derive new ways to self-organize the network and for matching and retrieval. Yeah, thank you very much. Wonderful question.
Just want to ask a clarification question. I don't quite understand
Sure,
how
please.
this has to do with, I mean, the self-organizing network, or I mean, maybe there is a missing component here between the recurrence and Tarkin's theorem and this self-organization. I don't understand the linkages between the previous parts and this part. Maybe I think there was a slide which was related to how you actually embed networks. I think, and I was not very clear about how that embedding is related to Tarkin's embedding.
I have to say, in this talk, I try to cover a wide spectrum of my research. And in manufacturing, healthcare, in networks, recurrence, and also in the nonlinear dynamics. So what I did is, so basic idea is you have sensors. And the sensor give you data. And once you get the data, you can look at it from statistic perspective. What I propose is a different way to look at the data and geometric thinking of the data, and look at this, because it's dynamic data, it's actually changing over time. So you can embed it into the higher dimensional space. Then you can look at the different perspectives of the data. Of course, it does not preclude the traditional way to analyze from the data mining or statistic modeling perspective. But this is another way to do the statistic modeling and geometric thinking. So sensing is give us data, then we do the modeling. Modeling can be done in two different ways, and can be done multiple different ways. And then we extract information, then we support the, for me, I'm engineers and industrial engineers, so I do more from the control perspective, but we can also do from the decision-making and the optimization perspective. So that's what I call sensing, modeling, and optimization. We should keep it in a coherent framework. So then I cover I want to just expand the linkage between different components. So the first component is nonlinear dynamics. I want to give a premiere or dive into nonlinear dynamics, the fundamental difference from nonlinear dynamics thinking and traditional data mining thinking. And then based on the trajectory, we can look at the recurrence. Means we show up at different locations in the geometry or in the topology. And then how does it relate to system behavior? And the recurrence, because recurrence can also help us do the network, because network can be done with by counting the neighbors, and which can also be done by counting how many recurrences we have in the state space. And there is a different way. The self-organizing network, there are different applications. One way is to study the time series. Time series can be embedded in the state space. Then you can study from the network recurrence network perspective. And just now, when I show the animation, I actually showed a different paper that studies the engineering design more from the application point of view. Yeah. So that's how it is connected. There are network behaviors, recurrence behaviors, and and in the state space, and also there are different behaviors. There are fractal behaviors too. I haven't covered in this tutorial yet.
So maybe let me ask this
Sure.
clarification question. So what is the state space in self-organizing networks? This is the part I don't really quite connect. So which part is nonlinear dynamics in the self-organizing networks? This is the part I don't really connect.
Okay.
The second thing is that I do not know what each does, what our dynamics is representing here. So this is something that I probably not missing here.
Let me elaborate your question. Your question is how state space is connected with recurrence network. Is that the question?
I think it's in the self-organ. I mean, if I can paraphrase, maybe the first two. I think up to the last part, it's relatively clear that you're trying to find these recurrences.
Yes.
And, I think maybe in the self-organizing network, there's no time element. Is that what you're saying? So there's no time element, at least when we first look at the chair thing, it seems to be like a point cloud type of, not a point cloud, maybe just an adjacency matrix representation. So maybe the question is coming from, that seems different from like a time element, and maybe that's...
Oh, that's a very good question. Yeah. As I said, recurrence network can be used to study time series, and then the network will change over time. Then the dynamics will come into play. And but your question is more about the second part, point cloud, right? So
The
in
third
point
part, I guess.
cloud, where where dynamics emerge. So in point cloud, the chair, I have to say point cloud, the dynamics is actually the energy change from the beginning to the end when we converge. That is one way we can see the dynamics. The second thing, if you can say a chair doesn't change at a particular time, and yeah, that's right. But any 3D object, they will change over time. And then you will have another degree of dynamics. So that's what I'm trying to deliver, the dynamics in two different ways. Yeah.
So to summarize, you're saying that the actual derivation of the chair, you're going through different states to actually come up to this chair form. And so that is your sort of
Yeah,
your
that's a
evolution
self-organizing evolution.
is a kind of time factor, but in that way is similar to the previous ones.
Yeah, and also that this chair and also this chair are very similar, but there are different type of chairs and vary from chair to chair. There are also a different degree of dynamics.
And I still don't understand what I mean by convergence, because if you're talking about convergence, that means that my dynamics is already known. So if you don't have, and I guess the purpose is try to figure out what the dynamics are from the data. So my inputs are the data, and then output should be, according to my understanding, is input is the data, output is dynamics. But right now you're telling me that okay, I have this something converges. So actually you know the dynamics and try to show okay something converges. So this is something really in my mind. I don't really understand what exactly it is about. Is what's the input and what is output? What's the cause? What's the effect in this context?
So the question about input did also occur to me. So your input is going to be a particular chair's adjacency matrix, and you know it's a chair, but the algorithm doesn't know it's a chair.
Yeah.
And so it just has the adjacency matrix of a chair. And then that adjacency matrix would correspond to multiple possible 3D figures, and you're trying to find the figure that is the best fit to your adjacency matrix somehow. Yeah. So I also had along the same lines. Obviously, there's lots of details, I'm sure, but let me just check the time. But maybe you can answer that question if that's. Maybe you can spend one more minute on this. It is 2:00. So.
Okay.
Yeah.
That's a very good question, and but in general, I didn't quite get the question. So the question is, if there is a convergence, then there is no dynamics. Is that a question? If the energy converge, right? If we do the calculation, the energy converge, then there is no dynamics. And the second question is, what is the input and what is the output? Is that?
Yeah, it has probably to do with, and I think all of us understand it's kind of very fascinating, by the way. And I guess we're just asking for more details, and I think that's how it started.
Sure.
But yeah, so I understand if it's difficult to convey all of it in a short time, obviously. If you had one final thoughts on it, then we could sort of maybe you could point us to a paper. Maybe that could be another. Yeah.
Oh, okay.
Yeah.
So there are different levels of papers to describe the recurrence-based complex networks.
I see.
And I have to say, people study networks from different perspectives, but this network approach is focused on data. And I think the data is evolving over time. And if you look at the time series, for one segment of time series, we can derive the network data. And then the next window, the network will change. Yeah, but if we get the recurrence network, for example, you have a time series, and if you have one window, you can derive the network. Next window, you can get another network, and then this is another way to capture because the data is from a system. Then when the data change, when the network change, there is another way to monitor or study the system behavior. So that's where the dynamics. If you say the dynamics is from the system, and then it causes the data to change, right? And then it causes the network to change. And so that's one way that we can look at the dynamics. And the other way, if we look at the dynamics from the how the process, if we were just given the matrix, for example, this matrix, you don't know it is a chair or not, right? It is corresponding to this topology or the other topology. And as you are self-organizing the chair, and then you have energy variations. When I say energy, that's the network energy variations. So then when the energy converge, then eventually you got a stable structure. So you may call this dynamics, or you can call it, it is different, it's in a different term, but that's fine, but that's a process that we get it into the final shape.
So in the interest of time, we can move this offline.
Yeah, we can talk more offline.
Yes.
But thank you for the very good question.
Yeah. And I have a couple of more things I'll ask you.
Sure.
Let's thank the speaker one more time, and then thank you.